Hey kids, it's Mr. Cabley. Just wanted to say, hey, how you guys doing? And that I'm sure that by now I miss you and you guys miss me too. And I hope that you guys are working hard at physicsing and you're preparing for the exam, which will be at the end of this week. So, that said, let's go on with today's lesson, huh? So, today's lesson is about power. So, here's the definition of power. Power is the rate at which work is done. And basically what that means is the faster you do work, the more power you have. So this is the definition for power. This right here, the formula that you would see in your formula chart, power average equals work divided by time. And remember that delta time, what that just means is the amount of time that passes. So, if you start off at, 1 o'clock and you finish something at 2 o'clock, then the time that passes is 1 hour or 3,600 seconds. So that delta T is just the amount of time that goes by. The unit for power is watts. Yes, JJ watts, DJ Michael 5000 watts. You've heard of watts before. Specifically maybe on a light bulb. So the most typical type of light bulb is a 60-watt light bulb. There are so many different devices that measure their power in watts. So like your microwave in your house probably is a 1,000-watt microwave. You might have an electric dryer that might be up to 5,000 watts for an electric dryer. So watts are the unit of power. I want to say some word of caution, danger. Don't confuse work and watts. So it's easy, it's simple to tell the difference between work and watts. So W in a formula stands for work. As in work equals force times distance, work equals change in energy. And the unit for work is joules. W as a unit is watts, and watts are the unit of power. So here, like in this formula, P equals W over delta T. This is a formula. So the W in this formula stands for work. Right here, this W right there, that stands for work. So I do want you to just be really careful when you're writing the letter W. If it's W equals force times distance, that's work. If it's W equals change in energy, that's work. If it's the power equals 60 watts, that's watts. All right? So, other units of power. So you may have heard of horsepower. So I did some Googling. Here we go. 1 horsepower is 745.69 watts. So it's been said that the horsepower is the amount of power that a horse possesses. So if you're wondering, well, how much power does a horse have? A horse has 745.69 watts of power. So a little check for understanding here. Which would take more time to use 100 joules of energy, a 60-watt light bulb or a 7-watt light bulb? So you think about it. So it's asking how much time would each one of them take. And we can actually calculate a real number for that. For 100 joules of energy, so 100 joules, that's going to be the work that gets done by the light bulb. The work that a light bulb does is use up energy. So the work for each one would be 100 joules. The power for this type of light bulb is lower power than this type of light bulb. So this would be the 7-watt light bulb, and this would be the 60-watt light bulb. Because power equals work over time, time would be equal to work divided by power. So that'd be 100 divided by 7, and this one would be 100 divided by 60. So 100 divided by 60, let me do the math on that real quick. That would be 1.6 seconds, so pretty quick. 100 divided by 7, that would be 14 seconds. So, wow, this light bulb takes more time to use power. This light bulb uses power faster. So that makes sense, right? Because power is the rate at which energy is used, or the rate at which work is done. So the more powerful, the less time it takes to do work. The less powerful, the more time it takes to do work. So there we go. Back that up and play it again if you need to. Let's do an example, huh? So here's our first example. We have an electric motor. Here's our motor. It lifts a weight. There's our weight, which has a mass of 5 kilograms. So this is a 5 kilogram weight from the ground to a height of 1.5 meters. If it takes the motor 0.75 seconds, so that's our time, 0.75 seconds. To complete this, what is the power? Okay, so we are going to solve for the power. Well, I know that the formula for power is work divided by time. I have the time is 0.75 seconds. But what about the work? Do I have the work? Could I find the work? What formula should I use to find the work? So in order to answer this question, we have to calculate work. Well, in this case, I suggest that we use work equals change in energy. What type of energy does the weight gain by moving up? It gains gravitational potential energy. So the work that the motor does is to give gravitational potential energy. So the work is change in energy. That will be UG final minus UG original. UG final is the mass, 5, times G, 9.8, times the height, which is 1.5 meters, minus UG original, which is 5 times 9.8 times how high is it at the beginning? It's from the ground. Okay, so if it's from the ground, then that's a height of 0. So I guess it had actually 0 energy. All right, 5 times 9.8 times 1.5. Get my calculator out. 5 times 9.8 times 1.5. That is 73.5 joules minus 0. So the work done is equal to 73.5 joules. Okay, well then I can take that work and plug it in up here for the work. Work is 73.5 joules, and then I divide it by 0.75 to get the power. Okay, that's 98 watts. So the power of the motor, the power of the electric motor is equal to 98 watts. All right, so that is how you can use the formula to calculate power. And that one was straightforward. We solved for power. In the next example, you are given the power. So here we go. Next example, a 1,250 watt heater. Okay, you see that W as a unit? When you see W as a unit, that stands for watts. And watts are the unit of power. So the power is 1,250 watts. Okay, a 1,250 watt heater is turned on for 30 seconds. So the time is 30 seconds. How much heat did it generate? Well, okay, so let's talk about what kind of work does a heater do? The work that a heater does is to generate heat, right? So if the question is how much heat did it generate, really the question is how much work does it do? So what we're going to do is we're going to apply the formula P equals W over T to solve for work. To do that, let's actually just plug it in the formula. So 1,250, that's the power, equals work, that's what we're looking for, divided by 30. Okay, so to solve for W, we multiply by 30 on both sides. And 30 times 1,250 is 3,750. So 37,500 of work. What are the units of work? Oh yeah, joules. So 37,500 joules of work is the heat generated. All right, third example. This is a fun one. The Tesla Model S. That's a all-electric car, so it's the fastest production electric car. It has a 310 kilowatt electric motor. Okay, well, kilowatt. That's KW, stands for kilowatt. Kilo means 1,000. So the power of that motor is 310,000 watts because kilo stands for 1,000. So 310,000 watts. 310,000 watts is the power of that motor. Wow, that's a lot. How many horsepower is that? You could calculate how many horsepower that is, but we're not. Well, let's go ahead and do it. Actually, here. 310,000 watts to horsepower. Come on, Google. Aha. 415 horsepower. Wow, 415 horsepower is a lot of horsepower. Just to put that into context, my car has about 108 horsepower, so that's 4 times as much power as my car. All right, anyways, I got that 310 kilowatts off of the Wikipedia page for the car. Yeah, it says here, electric motor. You see that right there? Electric motor, 310 kilowatts, which is 416 horsepower. Just like we calculated on Google. All right, what was the question again? How much time would it take to accelerate the 2,100 kilogram Tesla from 0 meters per second to 27 meters per second? So we're going to be solving for time. Time is our question. Well, we know we're going to use power equals work divided by time to solve for time. In order to do that, we can change the formula, multiply T on both sides. So work, there we go, divide, and so then we have T times P equals W, divide both sides by P, and you get that T equals W divided by P. So we'll plug in the work that we find. To calculate the work done by the electric motor to accelerate the Tesla, we need to first think about which type of energy is going to be increasing. So we're going to use work equals change in energy. Which type of energy? Kinetic energy. So it's going to be kinetic energy final minus kinetic energy original. The final kinetic energy is going to be 1/2 times the mass, which is 2,100, times the final velocity, 27 squared. So bringing up my calculator, 1/2, that's 0.5, times the mass, 2100, times the velocity, 27, times 27, because you have to square it. Wow, okay. 765,450. 765,450. 765,450 joules minus the original kinetic energy, which is 0 because it's starting from a velocity of 0. So the work done is 765,450 joules. Great. Now to calculate the time that it would take, I just divide the work by the power. So time is work divided by power. That's the work. This is the work right here. Divide that by the power. Okay, the power is 310,000. So the time will be equal to 765,450 divided by 310,000, which is the power. That is 2.469 seconds. So 2.469 seconds. Okay, 2.469 seconds. That seems like a very short time to go from 0 to 60 miles per hour, which is 0 to 27 meters per second. But you know what? This car is really fast. So one last little bit I want to do is I want to show you guys a video of this car and just how fast it really is. Check this out. And also listen to the sound of this car. Wow, so as you can see, the Tesla is a very, very fast car. All right, so now the next thing that you guys are going to be doing is more practice problems. So practice problems about work. Hopefully you guys have already finished the practice problems about work, and you finished these practice problems too, the varied work problems for homework. And so now you guys, we did these examples, now you guys are on to this practice. So, good luck and study hard for that exam.